So I will be talking about integral affine geometry and degeneration of Calabi manifolds. And this is mostly joint work with Enrica Mazzon. So first, what do I mean by degeneration of Calabi manifolds? So I will define X over the punctured disk. This is going to be, so X is going to be a smooth complex manifold. So I will do everything in the Euclidean topology because I work over C, but most of it works over the, you can just replace D with the disk with a spectrum of a discrete valuation ring. So X is going to be a smooth complex manifold. Pi is going to be a submersion proper, that is proper, so the fibers are compact. So what do I mean by this is a degeneration of Calabi manifolds? I'm meaning that each fiber xt so xt I'm going to write as simply the fiber over t, t minus 1 over t, is a smooth Calabi manifold. So I'm just going to write cy. So it is compact, and by Calabi I just mean, to me, this means that the canonical line bundle is trivial. So this is quite the liberal definition. For instance, I am including a billion varieties, which is maybe not the usual thing to do, but it's just convenient because most of our results also apply to generate degenerations of a billion varieties. And I also want the family to be meromorphic at 0. So what do I mean by this? In some sense, I want the family to be algebraic. So it means that if I embed my family into some projective space times the disk, so I just embed my family into some large projective space times the disk, then I want the equations of xt to be meromorphic with respect to t. So I don't want the equations to have some crazy dependency on t. So the equations are meromorphic with respect to t. So I can just also clear the denominators, and it's not a problem. So, and for the talk, I will be mostly interested in the maximally degenerate case. So what does this mean? So this means that I want the xt to degenerate in the worst way possible. So the complex structure on xt is degenerating in some sense as t goes to 0, and I want this to happen in the worst possible way. For instance, this excludes the case of good reduction. So I will give a more precise definition a bit later on, but I will give a simple example that I will be using repeatedly through the talk. So I will look at something like x0 times x plus 1, xs plus 1, plus, so the dependency in t here is just here, plus t times some fn plus 2, which is just a generic equation of degree n plus 2, equals 0. So this is just a degeneration of hypersurfaces inside inside a projective space of dimension n plus 2. So this is in the n plus 1 times the disk. And what we can see is that in some sense, so those are Calabi-Yau hypersurfaces by adjunction. And as we can see is that as t goes to 0, they go to the reunion of n plus 2 coordinate hyperplanes. So the Calabi-Yau really breaks into many pieces, which are just affine spaces, I mean projective spaces. So in the maximally degenerate case, we have the classical SYZ conjecture. So this is a conjecture that is motivated by mirror symmetry mostly. So I won't be saying much about why and how we get this conjecture. But what it says, roughly speaking, is that for t close to 0, then the xt should admit a special Lagrangian torus fibration over some base b, which is a base of a real dimension equal to n, where n is the dimension of the xt. So in terms of real dimension, this is a base of which is half the dimension of xt, and it is just a topological manifold. So I'm not going to say what it means to be special Lagrangian, but it is a torus fibration which is smooth over some locus B naught inside of B. So over B naught, it is really a torus fibration, and I'm going to write delta as a discriminant locus, which is by definition B minus B naught. So this is where the fibration has singularities. And we want this to have a codimension at least 2. So this is what the conjecture predicts. This is mostly motivated by physics and mirror symmetry. So codimension of delta is greater than 2. So once again, I won't explain in much detail how we are supposed to get this fibration. But what I can say is that the structure it induces on the base. So in particular, it induces a Z-affine structure on the smooth locus. So what I'm writing as nabla Z. So this is a Z-affine structure. So what do I mean by this? Fine. Structure. So this is something that lets me make sense of what the Z-affine function is on B naught. So this is just an atlas of charts in a very differential geometric term, such that the transition functions are integral affine. With the transition functions, so those are integral affines. So they lie in GLN of Z. So those are affine maps, but with integral coefficients. And then I allow the constant term to be any translation. So it's something like this. So what this, in particular, this lets me define a sheaf of a Z-affine structure on B naught and etc. And this is a classical construction in symplectic geometry. So once again, this is not what I'm going to be talking today, how we get this, because I will be trying to reconstruct this affine structure in a completely different way. So the goal of this talk is going to reconstruct the base of the SYZ fibration together with its discriminant locus and the affine structure away from it, but using a non-Archimedean geometry. And hopefully, if I have time, try to explain how to construct a non-Archimedean version of the SYZ fibration. So this is NA. So instead of constructing the SYZ fibration in the real world, if that makes sense, we are going to try to construct it in the non-Archimedean world. And the idea that it should actually induce the same structures on the base, which are what we are interested in. So first, I'm going to talk about models and dual complexes of my degeneration X. So I'm going to say that curly X is a simple normal crossing model of X. So SNC stands for simple normal crossing. So here the total space is smooth once again. This is just an extension of X to the disk. So if I restrict my family curly X to the punctured disk, then I just should get the degeneration I started with. And I want the fiber over 0 to be a simple normal crossing divisor. So this is some sum I over I. Technically, I can allow some multiplicities, but You can also take them equal to 1 if you're more comfortable with it. Where the EIs are smooth and intersecting each other transversely. So I'm going to write this this way. So the point of working with models like this is that they are somehow the best thing you can get in general, since they always exist. So simply we embed X into projective space, then we take the closure inside the disk, and we get a model, and then what we do is just we resolve the singularities using Hironaka. So that they always exist, and there are a lot of them. So this follows mostly from Hironaka's theorem on resolution of singularities. So I'm going to say that a subset, a subvariety Y in the X0 is a stratum if there exists a subset of the set of irreducible components, such that Y is a connected component of some intersection of the irreducible components. So it's a connected component of some intersection of the EJs. So where big J is a subset of the irreducible components of the special fiber. And the point of this is that I'm going to define a combinatorial object attached to any model, which we call the dual complex. So the idea is that if I have a EI component inside the X0, so this is an irreducible component, I'm going to attach to it a vertex which I denote VI. And then what I'm going to do is if I have a connected component of EI intersected with EJ, I'm going to draw an edge between the vertices VI and VJ, and so on. And this way, I'm going to construct a cell complex. So I'm getting an edge, EIJ. So this is an edge from VI to VJ. And similarly, if I have a connected component of EA times EJ times IK, what I'm going to draw is a two cell. So I'm going to make a small picture. So I have my three vertices, VI, VJ, and VK. So let me just label them I, J, and K. So to have a component of EI intersected EJ, this means that I have some intersection here. So I'm going to have already three edges. And then for the connected component of EI intersected with EJ intersected with EK, I'm just going to draw a two cell like this. And so in this way, I'm going to get, in the end, a cell complex that encodes as the combinatorics of the intersections of the EJs. So to give you a more precise definition, so a stratum is once again a connected component of some non-empty intersection of components of X0, and then the faces of the dual complex are in bijection with the strata. In the incidence relation are just given as follows. So sigma y coming from a stratum y is a face of sigma y prime, if and only if y prime is a subset of y. So now this allows me to define what I mean by a maximally degenerate family. So I'm going to say that the family I started with, and here we don't need the Calabi hypothesis. So this means that for any SNC model curly X, I want the dimension of the dual complex to be maximal. So maybe I should have mentioned that, is that the dimension of this because of the simple normal crossing hypothesis, means that we always have that dimension of the dual complex is smaller than the dimension of the fibers over C, since we can only have n components that cut out a point. And so here I want this inequality to actually be an equality. And so this is what I said in a more heuristic way, that we want the xt's to break into as many pieces as possible. So now we have the following proposition. So obviously the dual complex heavily depends on the choice of models. But if we have two models together with a morphism from one to another, so what I mean by morphism of models is just that it induces identity when I restrict to X. So over the punctured disk, this is just the identity, and then some stuff is going on over 0. Then there exists a piecewise affine map, which I denote by R curly X prime curly X, from the dual complex of X prime to the dual complex of X. And even better, there actually exists a section, which I'm just going to write I. This is a section of R, and it is also an embedding. So in some sense, the dual complex of curly X prime is just bigger of R, and it's also a topological embedding. So when you move to a higher model, you only get a bigger dual complex. So I'm not going to give the precise definition of this map. So this is to define it, you really need to put coordinates on your simplices, and then you define using local equations of the GJs and some vanishing orders. So I'm not going to give the full detail, but I'm going to give a couple of examples of this map. So let's take x0 to be something like this. So just this is x0. It's just the reunion of two curves meeting at a point. So the dual complex, we have two vertices, and then we have an edge joining them. So what I can do is I can blow up the points here. So I'm just going to blow up the intersection point. And what I get is an exceptional divisor here that I can write as E. So when I look at the dual complex, this time I get 3 vertices and 2 edges. So I get something like this. And actually what happens is that here the map R is just identity. So the dual complex didn't change, but what changed is the triangulation. So blowing up here this point just amounts to doing a subdivision of the dual complex. So obviously the map I is also identity. There is nothing to explain. And then I can look at another example. So I start with the same x0. And then I'm just blowing up a general point here of the curve. Then once again I get a new vertex, but this time I will also get a new edge. So here once again I have the dual complex. And here, so I'm going to have my edge corresponding to the point here. And then I will have so this vertex comes from the exceptional divisor, and I'm having another edge right here. And so the retraction obviously just contracts this edge to the vertex here. And the inclusion I is also very easy to see. It's just we embed this interval inside this graph. So the point is that to prove this proposition, so here you can see that the proposition obviously seems pretty true, but that shows so the fact that here we have a section that is an embedding, it works very well in this case of example. But the point is that actually you can use some factorization argument to reduce to the case where this map is a composition of blowups, and then you just have to prove it for blowups, and pretty much the same argument as here. You just see explicitly how the blowups act on dual complexes. So to come back to my example from the start of hypersurfaces, so here I'm just looking at dimension 2. So this is a degeneration of K3s. So here we have that x0 is just the union of coordinate hyperplanes inside P3. So this x0, x1, x2, x3 equals 0. So the dual complex is pretty easy to see. We have 4 vertices. And for each pair of indices, we have one. So if I take 2 surfaces like this, x0 equals 0, x1 equals 0, they meet along a line. So we only have one connected component. And this is true for any of them. So we have something like this. So this is the one skeleton of the dual complex. And then similarly, we have a 2 face for each triangle like here. So it's simply the boundary of a tetrahedron. So topologically, this is maybe more the boundary of a 3 simplex. One remark is that here, actually, I'm cheating a little bit because this curly X is not a simple normal crossing. So you can check pretty explicitly that for generic F4, we have some singularities on curly X. So the singular locus is given by so you just take the gradient of the equation and look at where it vanishes. So it's a union of locus like this. So the singular locus lives inside the t equals 0, and then you vanish 2 coordinates, and f4 equals 0, and this gives you a. So this is a union of this over all the ij's. So this is just very explicit. So the point is that on each curve, xi equals xj equals 0 inside the special fiber, you should get 4 singular points because the f4 is of degree 4. And the issue is that di and dj, so maybe I write them ei and ej's, those are not a Cartier divisor at a singular point. So this is something I will come back to later. This will pose some issues. For instance, we cannot define the. So if I take a curly X prime, an SNC model dominating curly X, there does not exist a map like this. This is not well defined because this map is defined using local equations for my divisors. This map does not exist, and this is actually pretty annoying for some reason, so I will try to explain this by the end of the talk. But obviously, the singularities are mild enough that we can define the dual complex. So now, what does all of this has to do with the SYZ fibration? So the insight of Kontsevich and Seuberman was that the base of the SYZ fibration should be realized inside of these dual complexes. So in some sense, they all have a common part. So there should exist some kind of what I'm going to write d curly x essential. This is the essential part inside of each dual complex. So the dual complex heavily depends on curly x, but this is actually independent of curly x, and this is really something that is intrinsic with respect to x. So there is a way to define this inside each dual complex, but I will not do it because we are lucky enough to see that we will see that this is actually, in some sense, this is attained. So that there exists models such that the essential part is equal to the whole dual complex, so that I don't have to give the definition of this. So this is the content of the following theorem that I'm going to use as a definition. So this is due to Niquez, Shu, and Yu. So if curly x is a minimal model of x, So by this I mean in the sense of MMP. So obviously I'm not going to dive into any MMP today. So what this means is just that if you take the relative canonical divisor plus the reduced special fiber, but you can just ignore this if you assume that the special fiber is reduced. So this you can ignore if you're not comfortable with. We just want the canonical of curly X to also be trivial. So it is obviously trivial over the punctured disk because we have a family of Calabi-House, but we want the same to hold on the whole model. Then what we have is that actually the dual complex of curly X is equal to the essential part. And so this is also independent of a choice of minimal model. So this is going to be the part I'm looking at. This is, in some sense, this is the smallest dual complex you can get. So maybe I make a few comments on this. So the first thing is that the minimal models, they exist when we assume that X is algebraic, so defined over an algebraic curve. But they are not unique. But this is not a big problem because the dual complex does not really depend on the choice of minimal model. Then the second one that most people familiar with MMP should know is that curly X is not going to be an SNC model, so it's not completely. It does have some. The total space has some singularities, but the thing is that the singularities are mild enough so that we can define the dual complex without any issues. So I will just pretend that there are no singularities for now. And so the last point is that the dual complex of a minimal model is unique as a set, but the triangulation can depend on the choice of minimal model. So it is like before, when you blow up a point, when you blow up a strata point inside the curve, you're just subdividing the triangulation of the dual complex, and this is actually still a minimal model. So. Okay, so now I've been talking about dual complexes and the issues whether this heavily depends on the choice of models. So now, in some sense, what we are going to do is that we're going to take the limit over all the models that exist. So this is done using non-Archimedean geometry. So if my family X is a subvariety of Pn times the punctured disk, so the equations they are so that they depend on T, so that I can view them as a Laurent series of T. So what I'm doing is that I'm viewing X as a subvariety as Pn over K. So instead of viewing my equations as depending on T, I just say that the coefficients on the equation live inside of K, which is the field of Laurent series over T. So elements are something like this. So there are series that are finite on the left, and then you have something like this. And the coefficients are in C. And this happens to be a non-Archimedean field, since it has a non-Archimedean absolute value, which is just the exponential of minus order of vanishing at 0. So odd 0 of f is the smallest n, such that the corresponding coefficients is non-zero. So this is really, if you see this as a meromorphic function, this is really the order of vanishing at 0, or minus the order of the pole, but it's the same thing. So then so we have a variety over some valued field. So then there exists a theory, which is a Berkovich theory of analytic spaces, that gives us simply a Berkovich analytic space associated to X. So I'm not going to go into a lot of details here, and to me it will be mostly a topological space. So the Xn is associated canonically to X, So there exists a whole category of analytic spaces over K with the structure sheaf and so on, but I really won't be needing this during this talk. So I'm just going to talk about the topological properties. So it is a Hausdorff topological space. So this is not some Zariski topology or anything like this. I will draw a picture a bit later, and it's actually a space you can draw a picture of. So it is locally compact, locally contractible. And it happens to be compact if and only if X over K is proper, which is always the case for me today. But obviously, you can define this also when X is just a quasi-projective. So how is this Xn defined? So the points of Xn, in some sense, are valuations on the function field of X. So this is the field of meromorphic functions of X. So this contains as a dense subset the valuations Vx. So those are valuations on the function field of X that are restricted to the. When I restrict them to the constant functions, I just get my the valuation I started with, so odd 0. And often I'm going to pass from valuation to absolute value. So so the valuation is minus log of a non-Archimedean absolute value. So this is a non-Archimedean absolute value. So what is the purpose of this space for us? Is that actually it lets us realize all of those dual complexes in an intrinsic way inside of this big non-Archimedean space. So there is a way to embed the dual complex of curly X inside Xn. And I'm going to define the image as the image of this embedding. This is the skeleton of curly X. And so this is now as a space of Xn. So the idea is to realize the points of the dual complex as valuations on the function field of X. And moreover, this even provides us with a somehow explicit description of this space, since it is equal to the inverse limit. So I take the inverse limits over all the SNC models. So I have maps from one skeleton to another whenever there is a morphism of models. So I can take the inverse limits of all those simplicial complexes, and I actually get the space Xn. So I will draw a picture in a moment. And this also gives us a way to just simply associate it to this homeomorphism, a continuous map from the non-Archimedean space to each individual skeleton. And we will see that this is a very naive candidate for the non-Archimedean SYZ fibration. This was also the original idea of Kontsevich and Cyberman. So how do we embed this dual complex inside of Xn? So the idea is simply that if I have a Vi, a vertex of my dual complex, so this comes from EI, an irreducible component of X0. Then I'm just putting it, I just want to see it as a valuation. So I'd simply take the order of vanishing along DI. This is a valuation on the function field of X. So this is the way I embed the vertices inside Xn. And then there is a way, then we can interpolate between those valuations to embed each phase. So we do this phase by phase. For instance, if we have an edge Eij, we can embed it inside Xn as valuation. So I won't explain this in full detail, but there is a way of doing it that is fairly explicit. So let me move to an example that is somehow simpler. So this is just a family of elliptic curves. So I have a family of cubic curves inside P2. So I'm living inside P2 over the formal series over C. So what I want to do is just draw a picture of Xn. So here the dual complex, we have three vertices, V0, V1, and V2. So I'm going to draw them. And then we have so x1 equals 0 and x2 equals 0 have one intersection point. So I'm drawing an edge here. So for some reason, I'm drawing round edges this time because it will be more convenient for the rest of the picture. And so this is the dual complex of X. So this lives inside Xn. But then Xn is the inverse limit of over all models of the dual complexes. So what I can do, for instance, is I can blow up a point inside this curve and get an edge here. But then here I have a curve, I can blow up a point and get a new edge. And I can do this here. And I can also do weighted blowups and take any rational point here and get something like this, etc. And what I'm getting is actually, I can do any sorts of blowups, and then I take the limit of all the dual complexes. And so what I get is something that is, so there is this essential part, which is a circle. And over each rational point of the circle, there is an infinite tree. So those things are based at a point are trees. So this is actually a homotopic to the circle. So obviously it's not homeomorphic, but it's actually homotopic to the circle. And then over each rational point, I just have a tree. And the topology is fairly weak. So the opens are pretty large inside of this space. And this is the reason why we still get something that is compact. So this is just something to show you a picture. So now we've gotten to the stage where if X over the punctured disk is a family of Calabi-Haus, so we define its essential skeleton as the skeleton of any minimal model. So once again, this is something intrinsic that lives inside the non-Archimedean analytification of my family. And so what I want to do is to construct some kind of SYZ fibration, but in the non-Archimedean world. So this should be something like this: some continuous map from Xn to the essential skeleton. So then we will want a bunch of other structures. So we want this to be for instance, we want this to be a torus fibration away from a codimension 2 subset of this skeleton, which, by the way, is of dimension n because of the maximally degenerate assumption. So what is a non-Archimedean analog of a smooth torus fibration? So the only example we have is actually the torus. So if I take I'm going to write T. So this is just the algebraic torus over K. So something like this. The n plus or minus. Then the analytification of T actually admits a map that we can just write as val to Rn. And I'm just sending an absolute value Vx to minus log of my coordinates. So minus log of a T1, but with respect to the absolute value x. So remember that my point x is an absolute value on the function field of T. So I can evaluate my absolute value at the element T1, and like this up to Tn. So in some sense, this is just the non-Archimedean analog of the log of modulus map from C star to Dn to Rn. So this is really, you should really think of this as a non-Archimedean version of the following map. I'm just looking at C star to Dn. Then I have a map to Rn. Then I'm sending x1, xn simply to minus log of x1 minus log of xn. So I'm using minus log because it's evaluation, so it's a bit more natural, but you can use a plus log, it doesn't change much. And so you're formally doing the same thing, but in the non-Archimedean world, except here the point is an absolute value, and then you evaluate it at the coordinates. And so this will be the model for non-Archimedean torus fibration. So the definition is the following: if I have a continuous map from the non-Archimedean analytic space to some base B, I'm going to say that it is a torus fibration at x inside of B. If and only if we have a commutative square like this. So there exists an open neighborhood of x inside of B, such that we have a square diagram like this. So I have U like this. I map it to an open set in Rn, so I want this to be a homeomorphism. Here I'm having a rho minus 1 of U. Here I have my map rho. Here I want an isomorphism of analytic spaces. Obviously, I did not define what it is, but it doesn't matter. So it's more than a homeomorphism. It has to respect the structure sheaf and so on, but I don't want to go into too much detail. And so here, this is just val minus 1 of V, and this lives inside the torus. And here, this is just val. So basically, up to homeomorphism on the base and isomorphism on Xn, our map rho is just the val map. Like it's very simple. We just have a chart that tells us that our map rho is the same as this evaluation map. So it is a torus fibration. And so the point is that it also induces an affine structure on U simply by pulling back the sheaf of an affine structure on V. So maybe I should write it. So this induces a Z-affine structure. So once again, I'm just writing this as nabla Z on U, which is thus simply we pull it back of the one from Rn. So I'm just writing like this. So basically, a function on U, a real valued function on U is Z-affine if and only if, when I put it back to this homeomorphism, I get an affine map with integral slopes on this open of Rn. And so our first theorem is the following. So in some cases, this was done so in the case of a curve, this was done by Niquez, Xu, and Yu, and for the general case by Mazzon and myself. So I'm taking it. So here I actually don't need the Calabi hypothesis. So if curly X over the disk is a DLT model of a degeneration of projective varieties, I'm not defining DLT, but this includes S and C. So you can just assume S and C. And we want that the components of the special fiber are Q Cartier divisors. So up to some multiples, they are Cartier. Once again, if you can just assume S and C if you want to ignore the assumption of on the singularities. So it works for an SNC degeneration. And then I'm looking at a stratum curly x0 inside of curly x0, satisfying the following assumptions. So first, I want the variety z to be toric, but I want a bit more than that. So if delta z is the sum of ei intersected with z for the ei's that do not contain z. So I'm looking at the intersection of z with the other components of the special fiber. Then I want delta z to be precisely the toric boundary of z. So this is what I mean by the pair z delta z is toric. We want the co-normal bundle of z inside of curly x to be nef. And we want the intersection of z with any other connected components inside di to be connected. So this is a technical condition. Then what happens is that the row curly x from earlier is going to be a smooth toric fibration over the star of sigma z. So this is the union of faces of the dual complexes that contain sigma z. So I have my face, and then I look at all the faces that contain it. This gives me something of maximal dimension, and what we claim is that the row curly x is going to be an affinoid torus fibration over this. And we also have an explicit description of the affine structure on the star of sigma z in terms of the fan. What I'm just going to write as a big sigma z. So this is the fan of the toric variety z. So now I will give a couple examples to make this a bit clearer. So the simplest example is the case where z is a point. So let me look at my hypothesis again. So it is a stratum which is a point. So that this is always toric since a point is toric. This assumption is also empty, and the nef condition is actually not required because what we actually need is the higher cohomology of this guy to vanish. So on a point we actually don't need this hypothesis. So what we are saying is that simply then we have the star of sigma z. So sigma z. This is an n simplex. So this is of maximal dimension. So this is just sigma z, the interior of this. So what I'm saying is that I have a point which is the intersection of n components, and I have a maximal face like this. Then rho curly x is an affinoid torus fibration over this. So this was known for a while. This was already known to Kontsevich and Seuberman. This is actually not very hard to prove. It starts to be a bit more interesting when z is a curve. So the toric assumption means that our curve is a P1. So I have a curve like this, and with the fact that and it says that we have two components like this, D0 here that intersect C at a point P0, and then we have a second component of the special fiber that intersects C at a point P infinity. So at the level of dual complex, what does this mean? So we have the face sigma C, and what we're saying is that we have two components that intersect C. So this is basically drawing two simplices like this. So one on each side of the. So here we have a facet of the dual complex, and it is exactly between it is exactly the intersection of two maximal faces. So here we have the vertex V0. Here we have the vertex V infinity. And what we are saying is that on the interior of this union of two faces, then we have an affine torus fibration. And so this was used by Nikkei Shu Yu to prove that if curly X is a minimal model, then you can prove that every strata of dimension 1 is a P1 with 2 marked points. And so what this is saying is that on the neighborhood of each codimension 1 face of the dual complex, then we have an affine torus fibration. So rho curly X from X1, so this goes to the skeleton, is a affine torus fibration around each codimension 1 face. And so this is exactly what we wanted, right? Because we wanted the discriminant locus to have a codimension at least 2. So if I just define a delta is the 2 skeleton so I'm in the union of faces of maybe n minus 2. So this is a union of faces of codimension at least 2. Then we have this B naught, which is just B minus delta, and we have this nice codimension 2 assumption, and rho curly X is nice over this B naught. So we get that we have an affine torus fibration in codimension 1, which is exactly what we wanted. And so then the third example is when I look at an irreducible component of x0. So say I have my vertex VD like this. So I'm just drawing the 2-dimensional picture. So then I have a union of simplices that contain the point. So this thing is the star of VD. What we are saying is that when D is toric and with the assumption on the boundary, then we have an affine torus fibration around that vertex, so on that star. And what we can actually prove is that if I look at the neighborhood of VD with the affine structure, what we see is simply the germ at 0 of the fan of D. So in some sense, this is Z-affine isomorphic simply to the, so I'm realizing the fan of D. So this is the fan of D inside R2, so I get something like this. What I'm saying is that this thing embeds homeomorphically and preserving the Z-affine structure inside basically the fan of D. So I don't know how much time I have left.
I mean, we started a bit late, so why don't you take another 5 minutes or so and come to a good conclusion?
Okay, so I will try to explain what the real motivation behind this was. So it was mostly to study this example. So we did it in dimension 2 and 3, but for the purposes of the talk, I will just focus on the dimension 2 case. So we look at, again, this degeneration of hypersurfaces in P3. So where the dual complex is the boundary of a tetrahedron. So as I mentioned earlier, the issue with this is that we cannot define this retraction from the analytic space to the dual complex due to the singularities. So the local model for a singularity is at a singular point like this is xi xj equals tw, simply because, say, ij is 1, 2, then x0 and x3 are going to be units. So you can just remove them and you have xi xj plus Tf4 equals 0. So same if you take F4 as a coordinate. So if you say W equals minus E4 minus F4, you can see pretty easily that the local model for the singularity looks like this. So it's a three-dimensional ordinary double point. So what we want to do is we want to resolve the singularities of curly X. So there is a very naive way to resolve this thing. Simply, you can blow up the point 0. So I wrote this as a curly U. I can just blow up the origin inside a curly U like this, and get something with an exceptional divisor. So I have so if I just look at the dual complex of U, here I have a VI Vj. So this is the dual complex of a curly U. And then so I'm just blowing up. And what I'm doing is now I get a 2 simplex, VI Vj. And here I have a vertex associated to the exceptional divisor. But we can also do small resolutions, since actually, so it's the E in the exceptional divisor is a P1 cross P1 of this blow up, and so you can actually contract it along either one or the other ruling. So you can contract it in either direction. So here I have the blow up of U, and then I have 2 small resolutions. Here I'm contracting the P1 cross P1 in one direction, and here I'm contracting it inside the other one. So I get 2 maps like this, and then so if I'm drawing this in terms of dual complexes, there's going to be one retraction that looks like this, and the other one is going to look the opposite, so something like this. And the point of this is that we can choose, so we can actually preserve the. So if I write dj is xj equals 0, there is one resolution that doesn't change dj. So in the sense that the strict transform dj tilde inside, so the resolution which I write at u curly j, this is actually isomorphic to dj. So the point of this is I can do this for each of my so there are 24 singular points in total, and I can do at each point I can do the small resolution that doesn't change d0. So when I draw a picture, I get something where so I have the dual complex of curly X as I blow up the 24 singular points. So I blow up the 24 singular points, and then so I have the retraction associated to rho curly X tilde, and then I compose and then I do all the small resolutions. But what I'm doing is I'm always contracting in the direction opposite to V0. So I get something like this. And the upside of doing this is that here the strict transform of D0 is still D0. So D0, if you remember, it was just a P2 plus the sum of the 3 lines, L1, L2, L3. So it is toric. So we are in the context of our theorem. And so what our theorem says is that the retraction associated to this small resolution curly X0 is an affinoid torus fibration theorem. And so as a consequence, what we could do, and this is also something that was done by Kontsevich and Seuberman, is that we can cook up some kind of retraction like this. So I'm contracting all the additional faces of this big resolution obtained by blowing up the points. I'm just doing something very very combinatorial, and contracting every additional face explicitly like this. So something like this. And the point is that at this vertex V0, this looks exactly like the previous retraction. So this retraction, we knew it was smooth at V0. So here it will always be the case, but it's also going to be the case here at V1, V2, etc. So if I define my retraction like compose this map pi, so here I'm drawing the map pi with this is the retraction where curly X is the big blow up. Then this is an affine torus fibration near each vertex at the cost of introducing singularities along the edges. So as a consequence, we get a new retraction that is somehow more symmetric. For instance, in the Fermat case, we get something that respects the symmetry under the permutation group. And we actually get this in this way. The affine structure we get is what matches the old prediction of mirror symmetry. So it is something that appears in the Gross-Seibert program, that you want the singularities of the affine structure to lie on the edges rather than at the vertices. So in some sense, we were trying to make the non-Archimedean approach compatible with mirror symmetry literature. And so then maybe I should conclude. So I'm just going to say that we have so this construction was actually in the paper of conservative Cyberman. So this is a pretty old construction. And we were able to do something similar in dimension 3. So for generic family of quintic threefolds, we can do a similar construction. And what we get is an affine structure on the 3 sphere, which is exactly the one that occurs in the Gross-Seibert program, which is another approach to mirror symmetry, and that a priori has nothing to do with non-Archimedean geometry. So we were able to realize some of the constructions in this non-Archimedean setting. Okay, so maybe I should stop now.